Hey everybody, this is Johnny Cash, and we're going to talk about the central limit theorem here. First, we've got board problem 46. An SRS of 1,000 Americans found that 61% were satisfied with the service provided by the dealer from which they bought their car. An SRS of 1,000 Canadians found that 58% were satisfied with the service provided by the dealer from which they bought their car. The sampling variability associated with these statistics is A, about the same, B, much smaller for Canadians since their population in Canada is much smaller than the US population, hence the smaller the sample is a larger proportion of the population. That one doesn't even fit, you guys. Much larger for the Canadians since the Canadians have a lower population density than the U.S. Hence, the Canadians tend to live farther apart, which always increases sampling variability. That one doesn't make any sense either. They're about the same, you guys, because you're going to go whatever the standard deviation is. The sample standard deviation is going to be the standard deviation divided by the square root of 1,000, and these guys are both 1,000 right there, so they're going to be about the same. Okay. All right, so let's go ahead and do the central limit theorem. Here we go. Okay, central limit theorem, CLT. Draw an SRS of size n from any population, normal or even not normal. Doesn't even have to be normal, with mean mu and standard deviation r. The larger n is, the closer the sample distribution of the sample mean gets closer to the normal distribution of this normal mean, where this is my population mean, and this is my sample standard deviation, the population standard deviation divided by the square root of n. All right? Exponential distributions often look like, here's an exponential, sorry I did this with my finger on my little mouse pad here on my laptop. So that curve, that's an exponential growth function right here. Over here would be an exponential decay function, something decaying, like the life of a battery, you'll see in just a second. So they're not normal bell-shaped curves, but we're going to use these in our central limit theorem to do some calculations. It's all the same stuff that we've been doing. Okay, so the lifetime in service of electrical components and the time required to serve a customer or repair machines gives a density curve that resembles the second picture over here. Okay, so we're going to be talking about this one right here. All right, and that picture that I just circled right there is very non-normal. So the population is not a bell-shaped curve. It's strongly skewed to the right because it curves down to the right. And the most probable outcomes are near zero at one end of the range of possible values. Okay, makes sense. So the mean is 1 and the standard deviation is 1 just because. We'll talk about that later, but right now just because. So now we're going to look at figure 9.17 on page 522. Okay, the first part of it's here it's a distribution with one observation. Okay, remember the mean of this is still 1 and the standard deviation is 1, but now we're going to have n equal 1, and it looks like that. You see how that's very skewed to the right? Well, watch just when I increase it to 2, you guys, and then I think I increase it to 10 and then 25. So B, C, and D are the density curves of the sample means of n equals 2, n equals 10, and n equals 25. And so what happens is it starts making this highly skewed to the right curve more of a bell-shaped curve. Check it out with just n equals 2 right there. Boy, it just kind of lifts it right up right there. Check it out when n equals 10. Wow, exciting. Look at that. Bam, n equals 25. That is exciting stuff. But that's pretty natural, you guys. That's a natural bell-shaped curve right there, okay? So central limit theorem ensures that we can do some calculations there. Those are just the same graphs right there. N equal 1, n equal 2, n equal 10, n equal 25. Okay, and then notice as n increases, the shape becomes more normal and more of a bell-shaped curve. The mean remains at x equals the sample or the population mean, which equals 1, but the standard deviation decreases each time. As n increases, the standard deviation decreases. Because, you guys, when n increases, this denominator is getting bigger. And as the denominator gets bigger, it makes this fraction value get closer to smaller. It gets smaller and smaller and smaller. The bigger this gets, like think of this, you guys. 1 over 2 is 0.5. 1 over 20 is 0.05. 1 over 200 is 0.005. So the bigger the number is in the bottom, the smaller a fraction actually gets, okay? And since the standard deviation equals 1, that's why this equals 1 right here, you guys, from before, okay? Because it was given to us that it was equal to 1. All right, so here, central limit theorem allows us to use normal probability calculations to answer questions about sample means from many observations of any population, whether it's normal or not. Okay, so here we are servicing air conditioners. We're going to read the paragraph way at the bottom of page 522. Okay, the time that a technician requires to perform prevention and maintenance on an air conditioning unit, singular, is governed by the exponential distribution whose density curve appears in figure 9.17a. There it is, right there, because it's singular, n equals 1. The mean time is 1 hour, and the standard deviation is 1 hour. But your company is now going to operate 70 of these units, okay? So now it's just going to do just what we did yesterday, you guys. This, it's going to be the standard deviation, which is 1 over the square root of 70, and then everything else is the same. So here we go. Okay, so here we go. It's going to be 1 over the square root of 70, because this equals 1 right here. It says it equals 1 right there, okay? And then we want to know what's the probability that their average maintenance time exceeds 50 minutes. Okay, now these are in hours, so I'm going to have to convert 50 minutes to hours in the decimal, you guys, so that's easy. All right, so, oops, I forgot to put a 1 right there. 1 divided by the square root of 70 is 0.120. Okay, remember that's a 1 right there. All right, now let's just change that right now, just so I can be all smart here. Let's see, I want to go right there, and backspace, put a 1 in there. There we go. Okay, and so we get that 0.120. All right, so we want to calculate what's the probability that it's going to exceed 50 minutes. Okay, so now we got to convert 50 minutes to hours, you guys, because everything's in terms of hours. So 50 minutes is 50/60th of an hour, and that becomes 0.83333333. Keep saying it. Okay, so we want to know what's the probability that x is greater than 0.83. So this is, I'm going to do my z-score formula. This is my x and my z-score formula, the 0.83. So here we go. 0.83 minus 1 divided by 0.120. We calculated that because it was 1 over the square root of 70. So here's my z-score. I'm going to look that up in the book right there. And they wanted to know greater, you guys. So we want this side over here, and your book is always going to give you to the left, which is this 0.778. Alrighty, so you're going to do the 1 minus stuff action right there. Okay, so you get 0.9222. Alright, the exact answer, and I'm going to show you in a couple of lessons away, you guys, is 0.9294. You can do that in your graphing calculator under z-test if you do stats and z-test and do a z-score test. I'll show you that in a little while, you guys. Okay, and the central limit theorem is only off by tenths, hundredths, thousandths, by 7 thousandths right there.